All right. Um, Reviewing some database and SQL concepts with our buddy Gemini here. So let's see what we have here.
Database and SQL essentials for data science, data engineering, and AI engineering. A strong understanding of database concepts and proficiency in SQL are fundamental skills for anyone working with data, whether in data science, data engineering, or AI engineering roles. While the specific depth required may vary, the core principles remain crucial for efficient data handling, analysis, and model building. Essential database concepts. At the heart of data management lies the database. Understanding different database types and their properties is key to choosing the right tool for the job. 1. Relational databases. Concept. Data is organized into tables with predefined schemas where relationships between tables are established using keys. This structure ensures data integrity and consistency. Examples: PostgreSQL, MySQL, Oracle, SQL Server. Relevance. Widely used for structured data, analytical processing, and applications requiring strong transactional consistency. Data scientists often pull data from relational databases for analysis, while data engineers design and maintain these systems. 2. NoSQL databases. Concept. A broad category of databases that do not adhere to the traditional table-based relational model. They offer flexible schemas and horizontal scalability. Types. Document databases store data in flexible semi-structured document formats, e.g. JSON, BSON. Examples: MongoDB, Couchbase. Key value stores store data as a collection of key value pairs. Examples:
Hold on. So document databases, they are also NoSQL. All right. So JSON, JSON, Mongo, these are also NoSQL. All right. It's important to note that it's not just key value stores. So usually when we are thinking of NoSQL, key value stores are the first thing that comes to mind, key value pairs, but obviously there are other types.
Redis, Amazon DynamoDB. Column family stores store data in columns rather than rows, optimized for wide columns and distributed data. Examples: Cassandra, HBase. Graph databases represent data as nodes and edges, ideal for interconnected data. Examples: Neo4j, Amazon Neptune. Relevance: suitable for unstructured or semi-structured data, large-scale data storage, and applications requiring high availability and scalability. Data engineers often work with NoSQL databases for handling big data, while AI engineers might use them for storing feature stores or model outputs. 3. Schema. Concept. The logical design of a database, defining the tables, columns, data types, relationships, and constraints. Relevance. Crucial for relational databases to ensure data consistency and integrity. Data engineers design and modify schemas, while data scientists need to understand the schema to query data effectively. 4. ACID properties. Concept. A set of properties that guarantee reliable processing of database transactions. Atomicity. A transaction is treated as a single, indivisible unit. Either all operations succeed or none do. Consistency. A transaction brings the database from one valid state to another. Isolation. Concurrent transactions do not interfere with each other. Durability. Once a transaction is committed, the changes are permanent and survive system failures. Relevance. Essential for ensuring data integrity in transactional systems. Data engineers must consider ACID properties when designing and implementing database solutions. 5. Normalization. Concept. A process of organizing columns and tables in a relational database to reduce data redundancy and improve data integrity. It involves breaking down tables into smaller, related tables. Relevance. Important for efficient storage and querying in relational databases. Data engineers apply normalization techniques during database design. Essential SQL concepts. SQL, structured query language, is the standard language for interacting with relational databases. Proficiency in SQL is non-negotiable for anyone working with data. 1. Data types. Concept. Define the type of data that can be stored in a column, e.g., int for integers, varchar for strings, date for dates, boolean for true/false. Relevance. Choosing appropriate data types is recording. Data scientists and engineers frequently use joins. 6. Aggregations. Concept. Performing calculations on a set of rows to return a single value. Functions. Count, sum, avg, min, max. Relevance. Used for summarizing data, a common task in data analysis. 7. Subqueries. Concept. A query nested inside another query. Relevance. Used to perform complex filtering, retrieve related data, or use the result of one query as input for another. 8. Window functions. Concept. Perform calculations across a set of table rows that are somehow related to the current row. They are similar to aggregate functions but produce a result for each row rather than a single result for the group. Examples: row underscore number, rank, lag, lead, AVG, over, sum, over, relevance. Powerful for performing analytical tasks like calculating moving averages, ranking results.
So this sum in the window function, this is different than this sum aggregations, sum over, average over. Okay, we'll see. Um, Interesting. So here again, create table, alter table, select, insert, update, delete, grant, revoke, um, inner join, left join, right join. These things does not have like any. These things are not considered as functions, more like commands. Um, I have to revisit the inner working of this, but anyway, let's move on.
Or comparing a row to preceding or following rows. Increasingly important for data scientists and engineers for advanced analysis. Common database and SQL questions and examples. Here are some common questions and examples relevant to data science, data engineering, and AI engineering roles. Scenario. Consider two tables: orders, order underscore ID, customer underscore ID, order underscore date, total underscore amount, and customers, customer underscore ID, customer underscore name, city. Q1.
So two tables: orders have 4 columns and customers have 3 columns. Order ID is the assuming primary key of orders, and customer ID is the primary key for customers. Okay, let's move on.
Retrieve the names of customers who have placed orders. Concept illustrated. Join for combining data from two tables and distinct to get unique customer names. Relevance. Basic data retrieval.
So here we'll select distinct c.customer name from customers.c, join orders O on c.customer ID equals o.customer ID. So unique, we are getting the unique customer names who has placed orders. Retrieve the names of customers who have placed orders. Alright.
And joining. Essential for all roles. Q2. Find the total order amount for each customer. Concept illustrated. Join and sum with group by for aggregation. Relevance. Common data aggregation task for analysis, data science, and reporting, data engineering. Q3. Get the details of orders with an amount greater than the average order amount. Concept illustrated. Subquery to calculate the average order amount and
So here we have total order amount for each customer. Sum ordered total amount as total ordered amount. So now we will have the response will be as 2 columns, one with the customer name and other with the total ordered amount, which will be the sum of ordered where from customer to C, where we are doing the join operation once again on customer ID, and we are grouping by c.customer name. Hold on just a second. Group by, where is there's one here, sum over, which used with together with over, and there's here when it is used just as sum, it is considered aggregation, and here when it is used as sum over, it is considered window functions. Alright, fair enough.
use it for filtering. Relevance. Using subqueries for more complex filtering logic. Q4. Rank customers based on their total order amount. Concept illustrated. Window.
Oh, okay. Missed the question 3. So Q3 is pretty straightforward. Give the details of orders with an amount greater than the average order amount. Select all from orders where total amount is greater than select average total amount from orders. So the average is being calculated within one query, so it is nested within the query select all from orders. Okay, let's continue.
Function rank for ranking based on an aggregation. Relevance. Advanced analytical technique using window functions, useful for data scientists and engineers. Q5. Explain the difference between a left join and an inner join. Answer. An inner join returns only the rows where the join condition is met in both tables. A left join or left outer join returns all rows from the left table and the matched rows from the right table. If there's no match in the right table, null values are returned for the right table's columns. Relevance. Understanding join types is critical for correctly combining data. Q6. How would you handle missing values in a SQL query? Answer. Filtering them out using is null or is not null in the where clause. Relevance. Data cleaning and preparation is vital before analysis or model training. Q7. Describe the concept of an index and why it's important. Index is a data structure that improves the speed of data retrieval operations on a database table. It's similar to an index in a book, allowing the database to quickly locate rows without scanning the entire table. Indexes are crucial for query performance, especially on large tables. Relevance. Database performance optimization is key for data engineers and impacts the efficiency of data access for data scientists and AI engineers. Q8. How would you add a new column to an existing table? Concept illustrated. Alter table with ADD column for schema modification. Relevance. Data definition language, DDL, for managing database schema, primarily a data engineering task. Q9. Explain the concept of ETL, extract, transform, load, and how SQL is used in each step. Answer. Extract. Reading data from source systems. SQL select statements are used to extract data from databases. Transform. Cleaning, transforming, and aggregating data into a suitable format for the target system. SQL is heavily used here for aggregations, joins, data type conversions, and data cleaning using functions like case, coalesce, etc. Load. Writing the transformed data into the target system, e.g., a data warehouse. SQL insert statements are used to load data into tables. Relevance. Fundamental concept in data engineering and data pipelines that feed data for data science and AI. Q10. What is the purpose of a primary key and a foreign key? Answer. Primary key uniquely identifies each row in a table. Ensures data integrity by preventing duplicate rows. Foreign key. A column or set of columns in one table that refers to the primary key in another table. Establishes a relationship between tables and ensures referential integrity. Relevance. Crucial for designing relational databases and maintaining data relationships. Relevance across roles. Data scientists need to proficiently query data for analysis, feature engineering, and model training. Understanding database concepts helps in understanding data sources and their limitations. Data engineers responsible for designing, building, and maintaining data pipelines and databases. Deep knowledge of database concepts, SQL, and performance optimization is essential. AI engineers often work with large data sets and need to efficiently retrieve and process data for model development and deployment. Understanding how data is stored and accessed is crucial. In conclusion, a solid foundation in database concepts and SQL is indispensable for professionals in data science, data engineering, and AI engineering. These concepts and skills enable efficient data handling, accurate analysis, and robust data-driven applications. The examples and questions provided offer a glimpse into the practical application of these principles in real-world scenarios.